Hello everyone, welcome to the presentation of our paper CommonUppRoad. It is a framework of formal modeling, verifying, learning, and visualization of autonomous vehicles. My name is Rong and I'm from Mälardalen University in Sweden. This is a joint work with my colleagues Kaige from Kaige in Sweden, Andreas Petersen from Aalborg University in Denmark, Lei Feng from KTH, and Kim Larsen from Aalborg University in Denmark. In the beginning, I'd like to talk about the state-of-the-art reinforcement learning platforms like the OpenAI Gymnasium. It is written in Python, and it provides you the Python modules or functions that you can use to develop your own learning algorithms and to solve the classic reinforcement learning problems, and even to upload your results to compete with other scholars or other practitioners. Uh, Also, there's another platform called CommonRoad. It is dedicated to autonomous driving environment. Here, they have a well-defined structure to describe the scenario of traffic, and they have tens of thousands of scenarios in their database, and these scenarios are converted from the real-world traffic scenarios. They also use Python, and they have predefined modules where you can use them to do motion planning, to check your result, for example, a lot of functions. And if we think of these platforms together, there are some questions to ask, like, do we know if the agent model, like the vehicles, are they correct or not? Like if their behavior match the expectation that is described in our specification of the system. We don't know that, and we want to know if the reward function is good enough, such that we can have an efficient learning, we can have a safe course of learning, so on and so forth. And also we want to know if the learning result is safe and efficient. If we want to really use the learning result in the final product of the AD vehicles, we must be sure that they are safe, and we want to know if they are efficient, because the safest plan, the safest controller is to make the vehicle stand still, but it doesn't go anywhere and doesn't accomplish anything, so it doesn't make sense. So we want it to move. We want it to move as fast as possible, but still keep it to be safe. This is the goal, but it's very hard to answer these questions in the current platforms. So in this presentation, I'm going to talk about formal methods and what the benefits we can get and how we can conquer the difficulties of using formal methods in the context of AD vehicles. Well, let's say somehow we get the formal models. It includes the models of the environment, the vehicles, the roads, traffic signs, all the elements that you can think of. We have already gotten the model, the formal model. And what's the benefits? Well, first let's look at verification. By using formal models, you can know if the vehicle behavior are correct or not. You can know if the sensory errors are too much, so you may have inevitable errors, inevitable collisions on the road. And you may wonder if one can do that without using, do these two things without using formal models. Sure, maybe they can, but what formal methods or formal models give to you is two things. One is automation, right? If you have the formal models, what you need to do is just to click the button to do the verification, and the model checker is gonna explore the state space for you and find out the bugs. Not only the bugs, but also the cause that leads to the bug. Everything is automatic. And second, if you have a very complex system where you put all the subsystems into one model, like you have a lot of vehicles in one scenario, you may have some emerging behaviors that you have not considered yet, and they appear just because the integration of all the subsystems. And if you have a formal model, the model checker can automatically discover these emerging behaviors and reflected in the counter example, for example. Also, we can get to know if the reward function good enough, if the discretization granularity good enough, because we don't want it to be too fine, so it increases the complexity of the learning too much, and we don't want it to be too coarse for sure, because it may, coarse granularity may miss some critical frames that may contain collisions even. And also we need to know if there exists a controller, a valid controller in the state space before we run learning, because learning is time consuming, right? If we run learning without knowing if we have the answer or not, we could totally waste the time. And for the controller synthesis, here we mean from the requirement, we want to automatically generate a controller that satisfies the requirements. So to do that, if we use formal models, we can deepen our understanding of the system. Like I said, we can even analyze the behavior of the vehicles step by step, and we can use verification to know if there are some unexpected behavior of the of the vehicles before we do synthesis. And we can make sure the learning process as well as the result are safe. And we may have, state space explosion problem if we use formal methods, but if we combine it with like reinforcement learning, we can alleviate the issue of scalability somehow. So these are the benefits. Now the problem is, how do we get the formal models? People who are reluctant of using formal models are always complaining that it is too hard to learn formal models. It is too hard, too time consuming to build the formal models. So how can we, solve this problem, encounter this difficulty? Well, we as the researchers in the community of formal methods, we want to solve problems, find the suitable problems to solve by using our methods. It's like we are holding a hammer and we want to find the right nails. But sometimes it is just hard to find the nails, or even we don't know where are they. Like in the context of AD vehicles, if we want to solve the problems that I mentioned in the previous slides, first of all, we need to know what are roads, how to mathematically represent roads, right? And we need to know how to model weather and what the influence can weather do on the vehicles, and different shapes of vehicles, different even brands of vehicles. We need to model them. We need to model the behavior of people. Different kinds of people. Different people can be aggressive, can be conservative. We don't know. And traffic rules. Different countries have different traffic rules. How do we model them? Or how do we even know them? Right? We are just, formal method guys. How do we know these things? And that's why we want to borrow the knowledge from other domains, like CommonUppRoad. It is a well-known platform for motion planning in the domain of autonomous driving vehicles, for example. It has all kinds of scenarios, and they are all converted from the real-world traffics, but you can also define your own scenarios. It contains roads, traffic signs, trajectories of other vehicles, so on and so forth. It also gives you the vehicle models, the vehicle parameters. They have different kinds of vehicles, even different brands of vehicles that we can use to build our formal models. And that's why we use it in this presentation, in this paper. And this is an example of a scenario. And they define the XML file for the scenario, where you can see on the right, you can see the clear structure of the roads, different lanes, and which one are adjacent to which ones, and so on and so forth. A lot of things can be reflect in this XML file of the scenario. And what we want to do here is to build the formal model for this scenario. So we can do motion planning, we can do verification, all sorts of things in the formal models. And the tool of formal model that we use is called UPO. Well, I guess everybody here knows UPO. You can do modeling, you can do simulation, you can do verification in one tool. And in the latest version, they also have reinforcement learning in UPO. If you want to do learning, the modeling language you use is timed games. If not the classic modeling language timed.mata in UPO. But timed games is very similar to timed.mata. It just distinguish actions into controllable actions and uncontrollable actions. Actions, you can think of them as transitions in timed.mata. Like here, it is the model of ego vehicle, autonomous vehicle. They are different words, but they are the same thing. So in this ego vehicle model, we have 3 kinds of actions: acceleration, deceleration, or just go with no acceleration. All of them are controllable in the perspective of the ego vehicle. So they are modeled as the solid arrows here. And this picture shows you the model of a car in front of the ego vehicle. We call it the front car. So all the actions here now are uncontrollable in the ego vehicle's point of view, right? So they are modeled by the dashed line arrows in this model. And when we have a composed model of both of the actions, what we want to do is to win the game, win the timed game. And to win the timed game, I mean to select the good controllable actions in the system model. If we call the one on the left the system model, the one on the right the environment model, we want to create a controller for the system model. The controller controls the controllable actions. And then at the end of the day, no matter when and which uncontrollable actions take place, the controller can always guarantee my system model to satisfy the requirements, like to be safe, or to reach the destination, or to be always above a certain velocity, so on and so forth. So this picture shows you a symbolic state space of the timed game. And it is called symbolic because we use zones here. You may know that in UPO they use zones to represent the infinite values of time. And here the zones form this symbolic state space. It is finite and it is countable. Like in the initial state 0, it can go to the state 1 on the left or state 2 on the right via these 2 controllable actions. And on state 2, for example, we have only uncontrollable actions, the dashed line arrows. So the model may go to state 5 or state 6, so on and so forth. If it goes to the red state, it is unsafe. If it goes to the green state, it is the go state. All right. And now if we are talking about the controller, which is called the strategy in UPO, it's a function that takes in states. Here we are talking about the symbolic states, the concrete value of the discrete variables, and zones to represent the value of the continuous variables. We take in the symbolic states and we give you the action that you should do on the symbolic state. Like in the beginning, if you follow the strategy here, orange colored arrows, the model always chooses the action on the right to go to the state 2. And then on state 2, there are 2 uncontrollable actions, 2, 5, and 6. So there's nothing we can do by using the strategy because these actions are uncontrollable. So they're not taken into consideration in the strategy. But at state 5, the strategy tells you that the model should go to the right action because it goes to the green state. So we can, eliminate the ones that are not returned by the strategy. And at state 6, it has only one controllable action. So it always chooses this one to go. All right. And in UPO, they use this keyword control to call the algorithm to generate such a strategy. It is called a symbolic strategy, for example, because when you do that, you explore the symbolic state space, and exploration is exhaustive. So it's very similar to exhaustive model checking. And like in this query, explore the state space, and you find out the traces where it is no collision, and there's no collision, and there's no off the road, right? So it is guaranteed to be always safe. And you can also verify the generated strategy safe to see if it's always safe, right? But this is actually redundant because we know that it is guaranteed. The safety is guaranteed since the exploration is, like I said, is exhaustive. So the synthesis is sound and complete now. But what if we use learning? When we use learning in UPO, we use random simulation. And to do random simulation, we use the concrete state space. Concrete state space means that we use the concrete values of the variables. Now clocks are not represented by zones from 1 to 2. No, we use the concrete values, 1.1 for example. And then we sample a state, and then we randomly select an action to go, and then we know the action leads us to state 1, which is also a concrete state. So it's like a sampling process. And we also know the reward of doing that action at state 0. And I say the reward is +5. And then next we have uncontrollable actions, so we don't need to do anything, just to randomly, explore them. And then we get to state 3, where we choose to do an action that leads us to an unsafe state. So we give a minus reward, -10 to the state and action pair there. So gradually we gather all kinds of traces like this and their rewards. We put them into the learning algorithm. In UPO, they use Q-learning, for example, to calculate the scores of the state and action pairs. So a strategy here is a function that takes in state and action pair and gives you back the score of this pair. So at the end of the day, you may want to always choose the action that has the highest or the lowest scores. Like in this query, it means you maximize, max E means you maximize the value of the reward function here. So here, you always choose the score with choose the action with the highest score. And you can also use this query to run reinforcement learning under the control of the safe strategy, the symbolic strategy. Remember, the symbolic strategy kind of restrict the state space. It gives you a portion of the state space. So when you do learning under the control of this strategy, you only sample traces within this portion. And that's why the learning process and the learning result are all guaranteed to be safe. After learning, you can also use statistic model checking to check the probability of reaching the goal under the control of reach. And you can also use symbolic verification to verify if the strategy is safe or if it can absolutely go to the goal. But if you want to use the symbolic model checking, you are not allowed to use continuous variables in the learning query. All right, so now we know what UPO can do for us. Like I said, the problem is to build the model. And what we do here in this model is to write a Python program to convert the elements in CommonUppRoad, in the scenarios of CommonUppRoad, to the formal models in UPO, right? So basically, we built up the templates of timed games for all the moving objects in the scenario. And we also define the data structures of the static elements, like the landlets, the planning goal, the static obstacles, and then we declare them as the constant variables in UPO. So these variables, because they are static, and they are declared as constant variables, so they don't count in they are not counted in the state space of the model. All right, so this picture shows you the vehicle model, and we have 3 components. If you look at picture A, it is the current module. You can think of it as a scheduler. All right, it calls other functions, other modules periodically. Like in the beginning, from a location L0, it goes to L1 via this edge labeled by eagle exclamation mark. This means this transition is synchronized with the transition on picture C, labeled by equal question mark. So they happen at the same time. And this means in the beginning, the scheduler tells the AD vehicle to choose an action. So it may choose to turn, may choose to accelerate, decelerate, or choose just to go. And after the AD vehicle chooses action, immediately after that, the obstacle can also choose the action via this edge, ops exclamation mark. And that is because our moving obstacles, they follow predefined trajectories. So they need to turn at each of the waypoints. So that's why we have this action. And after that, the concurrent module moves to a location L3 where time can elapse here, can elapse for a period time unit. And during this period, the continuous variables in picture B, they change. They change according to the ordinary differential equations here. This is basically the vehicle dynamics. X and Y, they are the coordinates, and so on and so forth. But since now we have the ordinary differential equations, we don't have the symbolic state space anymore, in theory. However, in UPO, they have these hybrid clocks. Hybrid clocks are only used in ODEs. They do not appear in guards or invariants. So they don't influence the behavior of the model. And that is why we can have ordinary differential equations and also the symbolic state space in the same model. Here it means that on the left we have the symbolic state space, on the right I have the number increasing, meaning that continuous variables are moving continuously. All right, and you can have them both in the same model, because the hybrid clocks, they don't appear on any like I said, guards or invariants, so they couldn't influence the transitions in the symbolic state space on the left. So when you run it, you just run the symbolic space step by step, and there's nothing the hybrid clocks can change in the symbolic state space. So that's why you can have them both in one model and run them together. Okay, and besides models, we also have some common functions defined for everybody to use, like off the road. We judge if the vehicle is coming outside the road, and we judge if two vehicles collide by looking at if these rectangles of these vehicles, they overlap or not. And we also judge if the vehicle comes into the go area completely. These functions you can totally reuse. And okay, now we go to controller synthesis and verification. So to do before we do that, we want to know if there exists a controller that is safe, for example. So that's why we use this query. E square, it means there exists one path where all the states on the path can satisfy the proposition, like no collide and no off the road. So if we can find a path that is safe, we can at least know that we may have a solution for controller. But maybe the uncontrollable actions can influence the behavior of the controllable actions. So the AD vehicle may be deviated from this path, this safe path. But the answer of this query at least tells us if you have an answer, a solid answer of controller or not. If you don't have any safe path, you don't need to run the learning next step at all. You save the time. Let's assume we have a valid controller, so we can do learning. I mean, here it's symbolic synthesis, and then we can do learning to do optimization, and then verification, like I said. So in this paper, we run two groups of experiments. In experiment 1, we want to show you the usability of the method. So we randomly select 10 scenarios from CommonUppRoad, and we run the Python program to convert these scenarios to our formal models, and we run the syntax check in UPO, and then we synthesize controllers, different kinds of controllers. You see the result here. All the generated models pass the syntax check, and also we can check the existence of the valid controller, so on and so forth. The maximum time is only like 30 seconds because we shorten the distance from the starting point to the goal, so it doesn't take much time. But here we only want to show you the usability, right? So it is enough to show you that the generated models are useful. And next, in the next group of experiments, we show you the scalability. Now we have the original setting of scenario 2, and we have all kinds of moving obstacles, the goal to reach, and we run the 3 queries. You see that when we want to synthesize the safe strategy, where we use symbolic exhaustive search, the computation time increases exponentially when the time steps increase linearly. Time steps means like when it's 10, the vehicles are only allowed to move 10 steps. 15, then it's allowed to move 15 steps, so on and so forth. But learning, both learning under the control of safe or pure learning, the computation time is okay. They increases linearly. So this is our observation. All right, and also we can use the platform to visualize the strategies synthesized by UPO. If you only use UPO, you have the strategy, but you don't know how the vehicle moves on the road. So now it's a low-hanging fruit in our platform, because you click the button, we give you the visualization of the strategy in the trajectory here. And this one shows you that if we only use learning and we don't design the reward function well, the vehicle can go off the road and go directly to the goal area because it is the shortest. So that this animation shows you the value of doing the pre-verification before you run learning. All right, conclusion. We have the platform CommonUppRoad. It can convert scenarios into formal models automatically, and it guarantees the correctness, syntax correctness. And strategies in UPO can be visualized, but when you use symbolic search-based synthesis, it encounters the scalability issue, but it gives you the safety guarantee. And if you use reinforcement learning, it doesn't have the scalability issue, but you don't have the safety guarantee anymore. So in conclusion, 4 methods can strengthen RL, reinforcement learning, in the AD controller synthesis and verification. And our platform combines the powers of these 2 methods. Thank you very much. If you want to know more, please scan the QR code on the right bottom. Thank you.